All right, guys, in this video, we're going to talk about minimizing cost. So a manufacturer needs to produce a cylindrical container with capacity 1,000 centimeters cubed. So that gives us the volume. The top and bottom of the container are made of material that costs 5 cents per square centimeter, while the side of the container is made of material costing 3 cents per square centimeter. Want to find the dimensions that are going to maximize the company's, or excuse me, minimize the company's cost of producing the container. So we have a picture here that kind of shows the cylinder that we have here. And then if you slice it down one side and lay it flat, the lateral surface area that goes around the sides ends up being a rectangle. And so the lateral surface area is 2 pi r times h, where r stands for the radius. The top is a circle, so its area is pi r squared, and so is the bottom. Okay, so the total area of the top and bottom is going to be 2 pi r squared um, for that one. And then the lateral surface area is 2 pi RH. Now we know that the volume of the cylindrical container is 1,000. And we also know that the volume of the cylinder is pi r squared h. Now we're not optimizing the volume. That's our constraint. We know the volume has to be 1,000. So we can set that equal to 1,000. This is what we would call our secondary equation. The primary equation is the cost. All right. But the cost deals with the area of the lateral surface area and the area of the top and bottom. Okay, because we're talking about the amount of material that we're going to use there. So if I want the cost function, okay, that's going to be 5 cents per square centimeter for the top and bottom. So it's going to be zero point 0.5 times 2 pi r squared plus the 3 cents times the lateral surface area, which is 2 pi r h. Okay. Now, the problem is this primary equation has two variables, the radius and the height. But the volume, our secondary equation, we can solve that for h. I'm going to just do that over here, which would be uh, h equals 1,000 divided by pi r squared. Okay, so we can simplify this a little bit by plugging the value of h in there and then simplifying some of our work here. So zero point 0.5 times the 2 is going to give us 0.1 pi r squared plus 0.03 times the 2 is going to give us 0.6 pi r times the h, which is 1,000 over pi r squared. Okay, so this is the function that we're going to minimize, and the domain is for the cost function is going to be r greater than 0. Okay, um, because radius can't be negative, and if it's 0, you wouldn't have a container. But you can theoretically, the larger you make the radius, the shorter the can's going to be. But we want to find the sweet spot that's going to optimize those dimensions so that the cost is minimized. So we take the derivative, so see, with respect to r. So this is going to be 0.2 pi r. Um, Now we got to simplify this 0.6 pi r, so the pi's are going to cancel, factor of r, and we're going to have 60 in the numerator for that one. So I did forget to simplify that. So this is going to give us, I'm just going to simplify this to 60 over r. All right, so the derivative, if you think of 60 over r, it's 60 r to the negative 1. The derivative is going to be negative 1 times 60 times r to the negative 2, or 60 over r squared. Okay, now I can get a common denominator and subtract those and rewrite this as 0.2 pi r cubed minus 60 over r squared. Now that sometimes helps to find critical numbers um, in this case here. So if I want to set C prime equal to 0, so I got to set this equal to 0. Notice it's undefined when C equals, or excuse me, when R equals 0, which doesn't really help us out because that's not part of the domain anyway. So essentially, we need to set the numerator equal to 0, 0.2 pi r cubed minus 60 equals 0. So r cubed equals 60 over 0.2 pi, okay, which is going to be, if I do 60 divided by 0.2, that's going to be 300 over pi. So r is the cube root of that, so that's cube root of 300 over pi. Okay, now we can use the second derivative test in order to determine if that's a relative max, relative min, or inconclusive. So what we can do is go back to the pre-simplified form of C prime to get the second derivative. So C double prime is 0.2 pi minus, or it's going to end up being plus 120 over r cubed. Okay. So C double prime, notice uh, 0.2 pi and 120 over r cubed are both going to be positive no matter what positive number you plug in for r cubed. So C double prime of cube root of 300 over pi is going to be positive. So by the second derivative test, if the second derivative is positive at a critical number, then you have a relative min. So at r equals cube root of 300 over pi, you have a relative min. So this is going to be the absolute min, and the radius of the container is going to be approximately 4.571 centimeters. All right. And then the height, because we need the dimensions, is 100, or excuse me, 1000 over pi times, times r squared. So cube root of 300 over pi squared. Now you could just dump that into Desmos or your calculator, and you would get 15.236 centimeters for that right there. And then the actual cost, so we can dump these numbers into the cost function. So cube root of 300 over pi equals 0.1 pi times cube root of 300 over pi squared plus 60 over r, which was cube root of 300 over pi. And then if we, again, dump that into Desmos or graphing calculator, you would round to the nearest cent because you're dealing with money is $19.69 for that one. All right. Hope that was helpful to you guys. Reach out if you have any questions. Take care.